Hybridization. You may recall from your General Chem 1 class that hybridization is simply determined by the number of things coming off of your central element. For instance, this tetrahedral carbon has 4 different directions emanating from it, and each one of the directions counts for an orbital. So you can use 1s orbital and you can use 3p orbitals to account for each one of the directions. There's 4 directions from the carbon and there is 4 orbitals here. So this is an sp3 hybridization on carbon, tetrahedral carbon. The same can be said for water. Water has a bent structure, but it does have 4 occupancies or 4 different things sticking out of it. Because of that, each one of the 4 things needs to be accounted for an orbital, thus yielding the sp3 hybridization. This is also true of ammonia and hydrofluoric acid. For fluorine, you have the sp3 hybridization because you have 4 things coming out of the fluorine, 3 lone pairs and 1 bond. Nitrogen, you have 3 bonds and 1 lone pair. And you could apply this to even more complex molecules. So hydrogens, those are always going to be s orbitals, right? There's nothing to hybridize there because they're in the first energy level. They only have the s orbital. The fluorines and chlorines have to have an sp3 hybridization so that you complete their octet. So notice here that I didn't draw the lone pairs, but it's understood that the fluorine and chlorine should have 3 lone pairs so that they have a full octet on them. Therefore, they have sp3 hybridization. Same thing can be said about the oxygen here. It's not drawn out, but it is understood that 2 lone pairs should be present on the oxygen so that its octet is fulfilled. Tin right here already has 4 bonds around it. It has a full octet, and it also has an sp3 hybridization as a result of 4 things coming out of it. The carbons over here, on the other hand, the first one right here has 1, 2, and 3 directions coming from it, so you only need 3 orbitals, therefore you have an sp2 hybridization, same as the carbon over here right next to it that has 1, 2, and 3 directions coming off from it, so you have the sp2 hybridization. The carbon on the very right side or the very far side of the molecule, it only has 2 directions, so 1 direction and 2 directions. And notice that it doesn't matter whether you have lone pair, single bond, double bond, or triple bond. Any of those counts as a single direction. So this carbon right here doesn't have 4 directions. It has 4 bonds, but it only has 4 directions coming from it. So you have an sp hybridization because you only need 2 orbitals to account for the 2 directions. The same is true for the nitrogen here. The nitrogen has to have a lone pair on it to fulfill its octet. Therefore, you have 1 and 2 directions on the nitrogen, also described by an sp hybridization. The second thing that needs to be said is that sp3 hybridization will have tetrahedral shape for those atoms that don't have lone pairs on the central element. It will have a bent structure for elements that have 2 lone pairs on the central element, and it will have a trigonal pyramidal structure for those elements that have a single lone pair on the central element. An sp2 hybridization, on the other hand, is indicative of trigonal planar shape, while the sp hybridization is indicative of a linear shape. And when it comes down to you guys drawing your Lewis structures, I'm definitely going to be strict about how you draw segments that should be linear, segments that should be trigonal planar, and segments that should be tetrahedral. If you don't draw them as such, especially if you draw a linear structure as bent, I'm going to have issues with that. So be careful not to commit that mistake. All right, now the thing that you may not have actually covered in your general chemistry course, which I'm going to explain right now, is the idea of hybridization in relation to how it relates to the bonds, the bond lengths, and even the strengths of the bonds themselves. And the idea ultimately has to do with what kind of hybridization we're dealing with, what kind of orbital we're utilizing the most. So As long as the bonds between the atoms are head-on, the orbitals form what we call a sigma bond. And in cases where we have p orbitals lining up side to side, we end up with a pi bond. All right, so this is the thing. When you're looking at a molecule, as long as they're single bonds, automatically those single bonds have to be sigma bonds. Okay, so you have a sigma bond between the sp3 hybridized bond of the carbon to the s orbital of the hydrogen. In your trigonal planar molecule right here that contains only 3 directions coming off from the carbon, you only need an sp2 hybridization. The sp2 hybridization implies that there is a third p orbital that's not being utilized. So you do have that p orbital just sitting there, waiting for something to happen. And as luck would have it, the element next door, which has an sp2 hybridization, will also have a p orbital that's not being utilized for the hybridization. So the hybridization forms a sigma bond. But then the two p orbitals end up coming together to give you a pi bond. And the idea right here is that one of the lines in your Lewis structure represents the sigma bond, the other line represents the pi bond. And you might have seen it drawn as follows, as a donut, around the two elements depicted, right? So you have a sigma hybridization and a pi hybridization. And the same thing can be said for a triple bond. You only have two directions coming out of that carbon, so you only need an sp hybridization, which means that you have two p orbitals that are not being utilized, and they are sitting there on that carbon. Same is true of the second carbon, which also has an sp hybridization. So you have, p going up and down, p going in and out, and both of those p orbitals form donuts of their own. You have the red donut here, which goes up and down, and then you have the blue donuts that goes in and out. So altogether, what you should get out of this is that one of the lines of the triple bond corresponds to a sigma bond, and the other two have to be pi bonds. So every connectivity you have will always have a sigma bond, but then any extra bonds due to multiplicity. So if you have a double bond, you have an additional pi bond. If you have a triple bond, you have two pi bonds in that same segment, but one of those lines will always have to be a sigma bond. So make sure to pay attention to that, especially if I do ask you to count how many sigma bonds and pi bonds are present in a structure, where you'll have to basically count every single bond, and then keep an eye out for those multiple bonds. And just remember that for the multiple bonds, um, one less than what you see is actually the pi bond. So you see two bonds here, only one of them is pi. You see three bonds here, only two of them is pi. Okay, so that's in terms of just counting the sigma and pi bonds in your entire molecule. But then there's another aspect that I was referring to earlier, and this has to do with how much S and how much P character is present in your hybridization. And the thing is this: S orbitals actually have a non-zero probability of being found at the nucleus. And it's a little bit counterintuitive, but this is part of quantum mechanics, and it's important to remember that the orbitals are nothing more than waveforms that are relating the interaction of the electron to the nucleus of the element. And for the s orbitals, there's actually very small. It's very small. You can see here it's very small, but it's not zero. A probability of being found at the nucleus. That is not true for your p orbitals or d orbitals, however. So this is actually a very unique property of these orbitals. And so with hybridization, what that would imply is that the more s orbital content your hybridized orbital possesses, the more positive charge that electron is going to see. And that has some implications that I'm going to depict in a moment. But first, let's think of this a little bit more mathematically. sp hybridization means that you have one s orbital out of two orbitals, right? One of them is s, one of them is p. So 50% of the character of this hybrid orbital is s. In an sp2 hybridized orbital, however, only one out of three orbitals is s, so you have only 33% character of s orbital in it. And for the sp3 hybridized orbitals, you only have 25%. So one thing that we will notice is that due to the geometries that we have based on sp3, aka tetrahedral structures, sp2 trigonal planar, and sp linear structures, we know that the angles are 180, 120, and 109.5, roughly speaking, for the different hybridizations. And so one thing that we're seeing is that the angles are becoming more opened up. They're more obtuse for the hybridizations that have more S content. All right, now in addition to this, because S orbitals can penetrate all the way to the nucleus and you're seeing more positive charge, there is a Coulombic attraction that's even more powerful. And that activity of the electrons to see more positive charge means that the electrons on the external atoms are seeing less, or not the electrons, but the atoms, the external atoms are seeing less electron density around them. In essence, you could say that having an sp hybridization makes the carbon more acidic than an sp2 carbon, than an sp3 carbon. And so what ends up happening is that your bond length tends to decrease because of that attraction to the nucleus. The bond association energy is also increased because your bond is even stronger as a result of the increased positive to negative charge combination. And as a result of removing the electrons away from your external atom, you could make things more acidic. So you could generate, organic fragments that can generate H pluses a little bit more easily than in other circumstances. We're going to take a look at that further down the line. All right, so here I want to show you really quickly how the bond lengths can be explained by the hybridization of the molecules. We have tetrahedral structures right here, ethane. We have a trigonal planar structure, ethylene. And then we have the linear structure, acetylene. And each one of them are determined to have sp3, sp2, and sp hybridizations respectively. Okay, so notice that the carbon-carbon bond length decreases as we go from sp3 to sp hybridization because we are increasing the S content of the carbon atoms. At the same time, the hydrogens that are bound to those carbon atoms that are going from sp3 to sp2 to sp are also decreasing in bond length. So you have an effect that is experimentally observed. And this is actually one of the powers of hybridization. So you could actually have a molecule like the one right here, where you have a bunch of double bonds, some triple bonds, and you have a lot more single bonds present. Now, generally speaking, triple bonds, as you see here, are shorter than double bonds, and double bonds are shorter than single bonds. But this is the caveat. Not all single bonds are the same. And the reason why is because the single bonds are being sandwiched by different types of hybridized carbons. All right, so the smallest thing is going to be the triple bond by default, followed by the double bonds. But now the single bonds is where the fun begins. Because depending upon whether the carbon-carbon single bond is between carbons that are sp3 hybridized or sp2 hybridized or sp hybridized, you have different amounts of electron pulling power associated with those carbons. And mathematically, it's actually not too bad because all you have to do is just consider the percent character. The percent character of sp3 hybridized carbons is only 25%, or in other words, you have a ratio of 0.25. If you simply add those ratios, 0.25 and 0.25 for sp3 hybridized carbons, you get a total 0.5 S character. If you do the same for sp3 and sp2, well, you have 0.25 plus 0.33, 0.33 coming from the 33% S character of sp2, and so on and so forth. And what you end up finding out is that there is a list of total S character for these combinations, and the greater the S character is, the shorter the bond is going to be. So when you look at carbon-carbon single bonds that are basically sandwiched between sp-sp carbons, like the one that you see right here, this carbon-carbon bond is between an sp and another sp carbon. That's going to be the next shortest bond. The next one that follows will be an sp2sp single bond carbon. So we have an sp carbon right here. That's an sp3, so it's not quite. This, however, is an sp carbon, and the one next door is an sp2. So this will be the next carbon, the shortest in line, slightly longer than 3. After that, we move on to the sp3. So we see that having that sp content is actually very crucial. Just having, even with an sp3, um, we still have a lot more s content than having two sp2s together, right? So the sp3 sp is found right here. You have your sp carbon over there, your sp3 carbon right here, and then your sp2s. This is basically the carbon-carbon single bond sandwich between two double bonds. So we can see that right here there is a carbon-carbon double bond, carbon-carbon double bond. So this is sp2, that's sp2, that's the next single bond in the series. Um, After that, we look for the sp3 sp2 component. So we're looking for double bond next to single bond, and here we go. That's a carbon-carbon double bond, so this is sp2, but then this carbon right here is sp3, so that's the next one in the series. And then the last one will be just a typical sp3 carbon to another sp3 carbon, which is found all the way right here, and that's indeed the longest single bond in the series. So you can actually observe this experimentally, so it's kind of powerful that hybridization allows you to see all those changes. All right, now in the next video, I'm going to explain how the hybridization relates to the bond angle relationship of the molecules. So see you there.